NENOMATICA, where mathematics meets YouTube excellence. In this example, we will solve a symmetric system using the sum and product method. Here is the example. Notice the structure. We know x squared plus y squared, and we know the product xy. Step 1. Use the identity for the square of a sum. We can express x squared plus y squared in terms of s, the sum x plus y, and the product p equals xy. Step 2. Substitute the given values. 25 equals the quantity x plus y squared minus 2 times 12. This simplifies to the quantity x plus y squared equals 49. Step 3. Take the square root. So the sum s equals x plus y is plus or minus 7. Step 4. For symmetric systems, x and y are the roots of the quadratic t squared minus st plus p equals 0. We'll apply this twice. Once for s equals 7 and once for s equals negative 7. Case 1, s equals 7. The equation becomes t squared minus 7t plus 12 equals 0. It factors as t minus 3 times t minus 4 equals 0, so the roots are 3 and 4. Therefore, the ordered pairs are 3, 4 and 4, 3. Case 2, s equals negative 7. Now the equation is t squared plus 7t plus 12 equals 0. This factors as t plus 3 times t plus 4 equals 0, giving roots negative 3 and negative 4. Hence the ordered pairs are negative 3, negative 4, and negative 4, negative 3. Example. We will solve a symmetric system step by step using the S and P technique. First, read the problem. Step 1. Isolate the square root term. Move it to the right side to get square root of x, y equals x plus y minus 7. Step 2. Square both sides to remove the square root. Then, expand the square on the right. This gives x, y equals quantity x plus y squared minus 14 times x plus y plus 49. Step 3. Rewrite the second equation using the identity x squared plus y squared equals quantity x plus y squared minus 2xy. Then simplify to get quantity x plus y squared minus x, y equals 133. Step 4. Introduce s for x plus y and p for xy. Substitute into both relations. Now set p from both equations equal and solve for s. We find s equals 13. Step 5. Step 5. Compute p using the formula we derived. Then solve the quadratic t squared minus st plus p equals 0 for the two numbers x and y. Therefore x and y. In this lesson, we solve a symmetric system using a clever substitution and the difference of squares. We start with the system. Notice the left equation already contains x plus y and the square root of xy. We will try to express the second equation using the same ingredients x plus y and xy. First, rewrite x squared plus y squared as the square of the sum minus 2xy. Then add the extra x, y to combine like terms. Now view this as a difference of squares. The first square is x plus y squared, and the second square is the square of the square root of xy. That factors into the product of two conjugates. From the first equation, the second factor, x plus y minus square root of x, y, equals 7. Therefore, the other factor must be 19, so that the product is 133. Add the two equations to eliminate the square root term. Twice x plus y equals 26, so eliminate the square root term. Twice x plus y equals 26, so x plus y is 13. Substitute back into the plus equation to find square root of xy equals 6, so xy equals 36. Now solve for x and y using the sum and the product. Let t be a root of the quadratic t squared minus 13t plus 36 equals 0. It factors into t minus 4 times t minus 9, giving t equals 4 or t equals 9. So the ordered pairs are 4, 9 or 9, 4. A quick check. Both pairs give 13 for the sum and 36 for the product, and 7 for x plus y minus square root of xy. Everything is consistent. Final answer. Final answer. In this lesson, we solve a symmetric system step by step. We are given the system x plus y y equals 2 plus 3 root 2, and x squared plus y squared equals 6. Our goal is to find all real pairs x and y. Because the equations are symmetric in x and y, we introduce two helpers, s equals x plus y and p equals xy. This lets us compress the system using identities. First equation becomes s plus p equals 2 plus 3 root 2. For the second, recall that x squared plus y squared equals s squared minus 2p. So we have s squared minus 2p equals 6. A neat trick is to double the first equation and add the second. 2s plus 2p plus s squared minus 2p equals 4 plus 6 root 2 plus 6. The p terms cancel, giving s squared plus 2s equals 10 plus 6 root 2. Complete the square on the left. Add 1 to both sides to form s plus 1 squared. Notice 11 plus 6 root 2 equals 3 plus root 2 squared. So s plus 1 squared equals 3 plus root 2 squared. Taking square roots gives two possibilities. S equals 2 plus root 2, or s equals negative 4 minus root 2. Case A, s equals negative 4 minus root 2. From s plus p equals 2 plus 3 root 2, p equals 6 plus 4 root 2. The quadratic for x, with some s and product p, is t squared minus st plus p equals 0. Its discriminant is s squared minus 4p. Here it is negative, so no real solutions in this branch. Case B, s equals 2 plus root 2. Then p equals 2 root 2. The quadratic for x is t squared minus st plus p equals 0. Solving gives two real roots, which are simply swapped for x and y. The two numbers with sum 2 plus root 2 and product 2 root 2 are root 2 and 2. Therefore, the solution pairs are x equals root 2, y equals 2, or x equals 2, y equals root 2. In this lesson, we will solve a symmetric system by following the exact step order shown in the prompt. Step 1. Write the system exactly as given. We have x cubed plus y cubed equals 152, and x squared y plus xy squared equals 120. Step 2. Multiply only the second equation by 3, then rewrite the system. This gives 3x squared y plus 3x y squared equals 360. Now place it back next to the first equation. Step 3. Add the two equations term by term. On the left we get x cubed plus 3x squared y plus 3x y squared plus y cubed. On the right, 152 plus 360 equals 512. Step 4. Recognize the binomial cube. X plus y all cubed equals the left side. Therefore, we have parenthesis x plus y close parenthesis cubed equals 512, which is 8 cubed. So x plus y equals 8. Step 5. Use the second equation to find the product x, y. Factor x squared, y plus xy squared as xy times x plus y. Then substitute x plus y equals 8. So xy times 8 equals 120, which gives xy equals 15. Step 6. Solve the symmetric pair x plus y equals 8 and xy equals 15. The numbers whose sum is 8 and product 15 are 5 and 3. Therefore, the ordered pairs are 5, 3 or 3, 5. In this example, we will solve a symmetric system of equations step by step, following the exact algebraic structure shown on screen. First, I will show the example and the given system. Step 1. Factor the sum of cubes. Then, substitute the second equation directly and solve for the sum x plus y. We have x cubed plus y cubed equals quantity x plus y times quantity x squared minus x, y plus y squared. Since x squared minus x, y plus y squared equals 7, this becomes x plus y times 7 equals 35. Therefore, x plus y equals 5. Step 2. Use the square of a sum identity to express x squared plus y squared. Then rewrite the second equation in terms of x plus y and xy. X squared plus y squared equals quantity x plus y squared minus 2xy. So x squared minus xy plus y squared equals quantity x plus y squared minus 2xy minus xy. Substitute x plus y equals 5 to get 25 minus 3xy equals 7. Solve, and we find xy equals 6. Step 3. Use the sum and product to find x and y. If t is a root representing x or y, Then t squared minus the sum times t plus the product equals 0. That gives t squared minus 5t plus 6 equals 0. Factoring, t minus 2 times t minus 3 equals 0, so t equals 2 or t equals 3. Therefore, the ordered pairs are 2, 3 or 3, 2. Finally, a quick verification shows both pairs satisfy the original system. 2 cubed plus 3 cubed equals 35, and 2 squared minus 2 times 3 plus 3 squared equals 7. The same holds when x equals 3 and y equals 2. This completes the solution. In this example, we will solve a symmetric system using the sum of cubes identity. The system is x cubed plus y cubed equals 7, and x plus y equals 1. Because the information mixes a sum, x plus y, with a cubic sum, we use the identity x cubed plus y cubed equals the quantity x plus y cubed minus 3x y times the quantity x plus y. We will place that rule on screen now. Apply the identity to the first equation and substitute the known sum. X plus y equals 1. Starting from x cubed plus y cubed equals 7, we replace x plus y by 1 to get 1 cubed minus 3x y times 1 equals 7. Now simplify to isolate the product xy. 1 minus 3x y equals 7. Move terms to get negative 3x y equals 6, so xy equals negative 2. With the sum and product known, we turn the pair x and y into the roots of a quadratic. T squared minus the sum times t plus the product equals 0. That gives t squared minus 1t minus 2 equals 0. Factor the quadratic. T minus 2 times t plus 1 equals 0. Therefore, the roots are t equals 2 or t equals negative 1. Because x and y are the two roots, the solutions are the ordered pairs 2, negative 1 or negative 1, 2. We will list them and make a quick check of the original system. Final result x equals 2 and y equals negative 1, or x equals negative 1 and y equals 2. This approach is powerful for symmetric systems. Use identities to convert to sum and product, then solve the companion quadratic. We will solve a symmetric system step by step, matching the classic method for symmetric systems. Here is our example. Solve for x and y. The system is x plus y equals 11, and xy squared plus x squared y equals 30. Step 1. Introduce the symmetric sums. Let capital S be x plus y and capital P be xy. Then we rewrite each equation using S and P. Step 2. Solve for S and P from the miniature system. S plus P equals 11 and SP equals 30. Construct a quadratic whose roots are S and P. T squared minus 11t plus 30 equals 0. It factors into t minus 5 times t minus 6 equals 0. So the roots are 5 and 6. Therefore, S and P are 5 and 6 in either order. Step 3. Case 1. If S equals 5 and P equals 6, then x and y are the roots of t squared minus 5t plus 6 equals 0. Solving gives t equals 2 or t equals 3, so the ordered pairs are 3, 2 and 2, 3. Step 4. Case 2. If S equals 6 and P equals 5, then x and y are the roots of t squared minus 6t plus 5 equals 0. Solving gives t equals 1 or t equals 5, so the ordered pairs are 5, 1 and 1, 5. Final answer. The solutions are the four ordered pairs, 3, 2, 2, 3, 5, 1, and 1, 5. Quick check for one pair. 4x equals 3 and y equals 2. The first equation gives 3 plus 6 plus 2 equals 11, and the second gives 12 plus 18 equals 30. Both are correct. In this lesson, we will solve a symmetric system using the sum and product method. Here is the system we want to solve. Because both equations are symmetric in x and y, we introduce two helpful quantities. Let capital S be x plus y and capital P be x times y. Rewrite each line in terms of S and P. First, x squared over y plus y squared over x equals the quantity x cubed plus y cubed over xy. Second, 1 over x plus 1 over y equals s over p, which is 1 over 3. Now use the identity for a sum of cubes. X cubed plus y cubed equals s cubed minus 3ps. Substitute that identity into the first line and clear the denominator. we get s cubed minus 3ps all over p equals 12. Multiplying both sides by p gives s cubed minus 3ps equals 12p. But we already know that p equals 3s. Replace p by 3s and simplify. S cubed minus 9s squared equals 36s. Move every term to one side and factor out s. We obtain s times the quantity s squared minus 9s minus 36 equals 0. From the second line earlier, s cannot be 0, so solve the quadratic factor. The quadratic s squared minus 9s minus 36 equals 0 factors as s plus 3 times s minus 12. Therefore, s equals negative 3, or s equals 12. Then p equals 3s gives p equals negative 9, or p equals 36. To recover x and y, solve the monic quadratic whose roots are x and y. T squared minus st plus p equals 0. First branch, s equals negative 3, and p equals negative 9. T squared plus 3t minus 9 equals 0. So t equals negative 3 plus or minus 3 root 5, all over 2. Second branch, s equals 12, and p equals 36. T squared minus 12t plus 36 equals 0, with a double root at 6. Therefore, the solution set consists of 3 ordered pairs. Either x and y both equal 6, or x equals negative 3 plus 3 root 5 over 2, and y equals negative 3 minus 3 root 5 over 2, or the other way around. The key idea was to exploit symmetry using s equals x plus y and p equals xy, convert the system, and then solve a single quadratic for s before recovering x and y. In this lesson, we solve a symmetric system that features reciprocals. We'll follow a clean algorithm. Clear denominators recognize symmetric sums, build the cubic with those sums, and then factor to find the solution. First, here is our example. Step 1. Write the given system exactly as stated. It contains 3 equations, one with single reciprocals, one with pairwise reciprocals, and one with the triple reciprocal equal to 1. Step 2. Clear denominators by multiplying each equation by x, y, z. This step must be done carefully for each line. Now cancel common factors to obtain the clean symmetric sums. We get x plus y plus z equals 3, xy plus xz plus yz equals 3, and xyz equals 1. Step 3. Recognize the symmetric sums as p, q, and r. If x, y, and z are the roots of a monic cubic, then p equals the sum, q equals the sum of pairwise products, and r equals the product. The corresponding cubic is t cubed minus pt squared plus qt minus r equals 0. With p equals 3, q equals 3, and r equals 1, this becomes t cubed minus 3t squared plus 3t minus 1 equals 0. Step 4. Factor the cubic. Notice the binomial expansion. It factors as left parenthesis t minus 1 right parenthesis cubed equals 0. So t equals 1 is a triple root. Because the cubic was constructed to have roots x, y, and z, the solution is x equals y equals z equals 1. In this lesson, we will solve a symmetric system by turning it into a simple quadratic. We will follow an easy algorithm, then apply it to a concrete example. Algorithm. If we are given a symmetric system of the form x to the n plus y to the n equals a, and x to the n times y to the n equals b to the n, then x to the n and y to the n are the 2 roots of the quadratic t squared minus a t plus b to the n equals 0. Example. We will now apply the exact same algorithm to the following system. The system is x to the 4th plus y to the 4th equals 8, and x times y equals 2. To match the 4th powers, we raise the product x, y to the 4th power. Since xy equals 2, we get quantity x, y to the 4th equals 2 to the 4th, which is 16. Now our symmetric 4th power system is x to the 4th plus y to the 4th equals 8, and x to the 4th y to the 4th equals 16. So x to the 4th and y to the 4th must be the roots of the quadratic t squared minus 8t plus 16 equals 0. Solve the quadratic. The discriminant is 64 minus 64, which is 0, so the equation has a repeated root t equals 4. Because t represents x to the 4th or y to the 4th, we obtain x to the 4th equals 4, and y to the 4th equals 4. Each variable, therefore, has magnitude square root of 2. Finally, we must satisfy the original product condition, x times y equals 2. The product is positive 2 only when x and y have the same sign. So the valid solutions are both positive square root of 2 or both negative square root of 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.